The interstellar explorer 3I Atlas recently accomplished a feat nobody foresaw. As it journeyed through its closest approach to the Sun on October 29, 2025, it unexpectedly flared in brilliance, adopting a hue more sapphire than our own star. This isn't conjecture. This is precisely what Avi's team has now validated, utilizing fresh readings from the Stereo, SOHO, and GO spacecraft. And here's the disquieting aspect. Loeb's research group concedes they cannot account for it. When Avi describes something as inexplicable, it signifies far more than a minor anomaly. The scientific community finds itself at odds. Some posit a highly unstable interstellar comet, reacting dramatically to the Sun's intense energy. Others entertain the notion of something far more peculiar, a component of fabricated material only activating under extreme radiative conditions. Regardless of the ultimate truth, one certainty remains. 3I Atlas has literally surpassed all prior expectations. Please stay with me until the conclusion, as tonight we will scrutinize these recent discoveries in meticulous detail. By the end, you will comprehend why humanity is utterly unprepared for what lies ahead. Because as 3I Atlas reappears in our view on December 19th, this time, it might be more than just a transient visitor from beyond our stellar neighborhood. If this enigma continues to captivate you as it has me, be sure to click like and subscribe so you don't miss a single update as this story unfolds in real time. Leave a comment indicating your location, the current time there, and your thoughts on this unprecedented development. And if you wish to contribute to the growth of this community, please share this video on X, Facebook, Reddit, or even within your group chats. Your support is the very reason we can continue to pursue such extraordinary narratives. Therefore, thank you for standing with us. Part 1. Breaking celestial news. Concealed behind the Sun, yet radiating with a bluer intensity than the Sun itself. October 29, 2025, marked the perihelion for 3I Atlas, the third verified extraterrestrial object to grace our solar system. One might assume this would be the primary narrative, a moment of celebration for another cosmic wanderer completing its closest pass by our star before rejoining the vast emptiness. However, what transpired instead has prompted seasoned astronomers to re-examine their instruments, meticulously recalibrate their equipment, and discreetly question each other about the very possibility of what they are observing. Multiple spacecraft coronagraphs have documented something entirely unprecedented. Stereo A's heliospheric imager and coronal camera, SOHO's LASCO C3 instrument, and GO-19's CCR-1 weather satellite have all reported the same astonishing phenomenon. The object's luminescence did not increase gradually, nor predictably. It erupted with a brilliance, following a scaling law that defies every established model of cometary behavior. The data reveals a narrative that should not exist, with brightness escalating with heliocentric distance to the power of -7.5, with a margin of error of 1. To put this into perspective, most comets brighten as they approach the Sun, adhering to a gentle power law, generally between -3 and -5. This is attributable to physical processes such as sublimation and the reflection of sunlight by an expanding envelope. However, a factor of -7.5 indicates something entirely different, not a comet warming up, but something else altogether, orders of magnitude steeper than anything in our archives of normal cometary visitors. Imagine this scenario. You are driving towards a destination, and as you draw nearer, you accelerate. The typical behavior of a comet is akin to a smooth increase in speed, transitioning from 50 to 60, then 70 miles per hour, a predictable linear acceleration. What 3i Atlas did near its perihelion is analogous to flooring the accelerator and observing your speedometer leap from 50 to 500 within seconds. A vehicle simply does not react in such a manner unless there is a fundamental difference in its very nature. And then there is the color. GO-19's CCR1 coronagraph recorded not only its luminosity, but also its hue. The photometric analysis revealed a color bluer than the sun's own spectrum. This was not a slight blue tint, nor an ambiguous shade. It was definitively and measurably bluer than the star it was orbiting. Coronagraph color indices are exceptionally reliable across multiple independent instruments. When Stereo A, SOHO, and GO all concur on similar observations, it signifies a genuine phenomenon, not an artifact attributable to a single sensor's peculiarities. The luminous halo extended approximately 300,000 kilometers in diameter, roughly 25 times the diameter of Earth. Envision enveloping our entire planet in a glowing shell and then placing 24 additional Earths side by side within that luminescence. That is the magnitude of what GO-19 observed. Furthermore, it was not merely reflected sunlight generating this envelope. The object appeared to be emitting light, projecting its own visible signature across wavelengths that would not be predominant if this were simply dust scattering. Here is where the situation becomes even more peculiar. 3i Atlas was obscured from Earth's view during this luminous display. Solar conjunction rendered the object invisible from our vantage point on the ground, lost within the sun's blinding glare to every telescope aimed skyward. However, spacecraft are not subject to this limitation. Coronagraphs are specifically engineered to block the overwhelming disk of the sun, enabling the imaging of the faint corona beyond. They can perceive what Earth cannot. On October 29th, while we were deprived of sight, our robotic sentinels witnessed an event that no human observer could directly perceive. The instruments had a front-row seat to a spectacle we are only now beginning to comprehend. Avi Loeb and his colleagues have presented these findings in recent preprints and publications, citing verified instrument data. The research paper adopts a deliberately cautious tone, as is appropriate. However, embedded within its technical prose is a sentence that should give anyone pause. The reason for 3i Atlas's rapid brightening, which far exceeds the brightening rate of most Oort cloud comets at similar distances from the Sun, remains unclear. When seasoned astronomers state that something remains unclear, they are not employing euphemisms. They are admitting that their established models are inadequate. The physics they rely upon proves insufficient. It is important to note that this research has not yet undergone peer review. Extraordinary claims necessitate extraordinary evidence, and the process of verification is still in progress. Instrument teams will rigorously examine calibrations. Independent analysts will request raw data frames. It is possible that an error will be discovered or that the observed trend will be unequivocally confirmed. Either outcome will profoundly influence subsequent developments. However, at this precise moment, we have multiple spacecraft conveying the same improbable narrative, and no one possesses a satisfactory explanation. If these findings hold true, we will not only be re-evaluating the nature of a single comet, but rethinking the very definition of what comets can be. We will be questioning volatile chemical processes we believed we understood and entertaining possibilities that, until yesterday, sounded like mere science fiction. Some of these possibilities involve exotic natural phenomena that we have never previously observed with such intensity. Others point to materials that simply do not occur in nature. I will meticulously guide you through precisely what the instruments detected, the significance of its bluer hue, the meaning of its brightness scaling laws, and the reasons behind the professional scientists' profound unease. We will dissect the data, explore competing explanations, assess calibration risks, and yes, delve into the wildest theoretical possibilities. By the conclusion of this initial segment, you will possess a comprehensive understanding of what has been reported and why it is generating such quiet apprehension within observatories worldwide. October 29th, 2025. Perihelion. Mark this date. What occurred behind the sun may herald the commencement of a narrative that redefines established principles, or it could serve as a cautionary account regarding premature conclusions. Regardless, Three-Eye Atlas has just performed an act that no one anticipated, and we have 5 weeks until it becomes visible again from Earth. 5 weeks to prepare for whatever may follow. The countdown begins now. Part 2. An in-depth instrument analysis focusing on coronagraph observations. 3 spacecraft, 3 distinct sensor systems, and 3 independent confirmations of the same improbable observation. Stereo A is equipped with 2 instruments pertinent to our discussion. The heliospheric imager, designated HI-1, captures expansive, faint fields at considerable distances from the Sun, tracking structures within the solar wind and occasionally documenting comets traversing its field of view. The coronal camera, CO2, provides a closer perspective, focusing on the inner corona where the Sun's atmosphere transitions into interplanetary space. Both instruments operate by effectively masking the Sun's direct light, thereby allowing them to detect objects that would otherwise be overwhelmed by solar glare. Consider it akin to shielding your eyes with your hand to spot a faint firefly positioned near a powerful spotlight. The spotlight remains visible, but you can finally discern the firefly. SOHO's LASCO C3 instrument has been diligently observing the solar corona since 1996. It is a seasoned veteran. Possessing a wide field of view and a less frequent image acquisition rate compared to modern sensors, it remains exceptionally reliable. With decades of calibration data and well-documented idiosyncrasies, when LASCO C3 reports an unusual brightness, teams are adept at cross-referencing its historical performance. This is not the case of a newly deployed instrument making nascent errors. GO-19, on the other hand, is primarily a weather satellite. Its CCR-1 coronagraph was developed to monitor solar eruptions for space weather forecasting purposes, not for the pursuit of interstellar comets. Featuring a high temporal resolution and low noise levels, it offers excellent precision in capturing events over time. When GO-19 documents a phenomenon, it does so frame by frame with a consistency that facilitates the identification of potential artifacts. Anomalies that persist across hundreds of sequential frames are rarely attributable to instrumental glitches. The geometric positioning is the reason why spacecraft coronagraphs can detect objects behind the Sun when terrestrial telescopes cannot. During solar conjunction, Three-Eye Atlas was obscured by the Sun's disk from Earth's perspective, rendering its line of sight entirely blocked for observers on the ground. However, spacecraft orbit at different locations. Stereo is positioned at a Lagrange point that affords it an angled perspective. SOHO orbits the Sun-Earth L1 point with a slight offset. GO-19 maintains a geostationary orbit, but its coronagraph is oriented outward, capturing objects at angular positions where the Sun's glare can be mechanically occluded. These instruments were not specifically tasked with observing Three-Eye Atlas. They simply happened to be observing the appropriate region of space when an extraordinary event transpired. Observation windows are critical. While perihelion occurred on October 29th, the instruments did not all capture data concurrently. Stereo A's HI-1 captures motion over extended periods, generating sequences that depict trajectory and changes in brightness. Core 2 provides more detailed snapshots as the object crosses its field of vision. LASCO C3 offers a broader but intermittent coverage, acquiring frames every few hours, contingent on telemetry schedules. GO-19 provided high-cadence monitoring, frame after frame, constructing a continuous record during the crucial hours surrounding its closest solar approach. The 300,000-kilometer luminous envelope was derived from GO-19 CCR1 data. Observers measured the apparent angular diameter of the glowing region surrounding 3D Atlas and converted it into linear kilometers using the object's known distance from the spacecraft. 300,000 kilometers is not a typographical error nor a misplaced decimal point. This is the documented extent of the diffuse coma captured in multiple frames. Comets are known to possess comas, and this is expected. However, the sheer size and luminosity of this envelope, coupled with its observed color characteristics, propel this observation into unprecedented territory. Color photometry, while technical, is of paramount importance. Coronagraphs do not merely record brightness. They employ filters to sample various wavelengths, thereby constructing a rudimentary spectrum based on the ratios of light within each filtered band. Sunlight exhibits a known spectral peak in the yellow range with a balanced distribution across the visible spectrum. By dividing an object's filter ratios by the sun's filter ratios, one obtains a color index. A positive index signifies a redder hue than the sun, while a negative index indicates a bluer hue. The measured color index for 3I Atlas during perihelion placed it firmly in the blue spectrum, not marginally or ambiguously so. It exhibited a greater proportion of short-wavelength light relative to long-wavelength light than the sun itself produces. Calibration is never perfectly precise. Stray light can scatter within the instrument, contaminating measurements. Vignetting can affect the uniformity of the detector's response across its field of view. Instrument response curves vary with wavelength in ways that necessitate meticulous correction. Background subtraction is as much an art as a science, particularly when attempting to isolate a faint moving object from the luminous coronal background. Any of these factors could introduce errors, potentially rendering a neutral spectrum artificially blue. However, the crucial point is this. All three independent instruments reported consistent trends. Stereo A, SOHO, and GO-19, each with different designs, distinct calibration histories, and operated by separate teams, converged on similar observations. When multiple sensors align on the same anomaly, the hypothesis of an artifact becomes considerably less plausible. It is not impossible, merely improbable. It would necessitate a conspiracy of errors, all biased in the same direction, affecting dissimilar hardware in precisely the same manner. This is possible, yes, but probable? That is where the debate truly begins. Raw coronagraph frames often resemble grainy black and white images with the sun's disk obscured by a circular occulting disk. Processed frames incorporate false colors to accentuate brightness variations and employ background models to isolate moving objects. When one plots brightness over time and superimposes data points from different instruments, the resulting curve emerges, a steep, alarming trajectory that should not exist for a typical comet. Standard comets exhibit brightening patterns following power laws around a factor of 4. Some can be as steep as 5. We have theoretical explanations for these phenomena: increased dust production, expanding surface area as fresh ice is exposed, and accelerated volatile sublimation. However, a factor of -7.5 signifies not a gradual increase, but a precipitous decline. If brightness normally doubles with a reduction in distance by 0.1 astronomical units, this object's brightness surged tens to hundreds of times more rapidly over the same distance interval. The mathematics are unequivocal. The physics we understand do not produce such a curve. Brightness alone does not convey the complete picture. An object can appear brighter either by reflecting more sunlight or by emitting its own light. Reflection is contingent on surface area and albedo, while emission depends on temperature and material properties. The color provides a crucial clue. While blue emission is not inherently impossible in a cometary context, it is highly unusual. Moreover, the intensity observed here exceeds what simple gas fluorescence should generate at these distances. Therefore, what precisely generated that ethereal blue light? This is the central question occupying every observatory that plans to observe 3I Atlas upon its reemergence. And every proposed explanation currently carries caveats, uncertainties, and assumptions that make professional astronomers deeply uneasy. We will now meticulously examine the brightness curve, piece by piece, to ascertain whether the numerical data truly supports this extraordinary claim, or if a simpler, less dramatic explanation lies hidden within the details. Part 3. Photometric and brightness curve analysis. Brightness scales with heliocentric distance raised to the power of -7.5 plus or -1. Let me elaborate on this statement, as it forms the crux of why astronomers are experiencing significant apprehension. Heliocentric distance denotes the object's separation from the Sun, measured in astronomical units. 1 AU represents Earth's average distance from the Sun, approximately 150 million kilometers. As a comet approaches the Sun, its heliocentric distance diminishes. As it recedes, the distance increases. Photometry quantifies brightness, typically expressed in magnitudes or flux units. The scaling law elucidates how brightness fluctuates with distance. For a standard comet, brightness increases modestly as it nears the Sun, often exhibiting a power law exponent of -3. This signifies that brightness triples when the distance is halved. An exponent of -4 indicates that brightness increases by a factor of 16 when the distance is halved. These represent the gradual curves we are accustomed to, those that align with sublimation physics and dust production models. A -7.5 exponent signifies that brightness escalates by a factor of 180 when the distance is halved. This is not a gentle increase. It is explosive. Constructing the brightness curve necessitates data from multiple sources. Pre-perihelion observations were obtained from ground-based telescopes tracking 3I Atlas as it approached, establishing the baseline. Subsequently, spacecraft coronagraphs captured the object during solar conjunction, providing the critical data points at perihelion. Analysts then plotted the logarithm of flux against the logarithm of heliocentric distance, fitted a line to these points, and determined the slope. That slope is the exponent, -7.5. The error bars are significant. Not every data point possesses equal reliability. Some frames exhibited higher noise levels. Others were affected by stray light or cosmic ray impacts. Some involved uncertain background subtraction. When fitting a line through noisy data, confidence intervals emerge. The plus or -1 applied to the exponent reflects this inherent uncertainty. The actual value could range from as shallow as -6.5 to as steep as -8.5. Regardless, this falls far outside the typical range. The convergence of multiple instruments on a similarly steep slope strengthens the claim. If only stereo A had reported -7.5, one might suspect an instrument-specific issue. If SOHO had reported -4 and GO had reported -9, one would conclude the data were inconsistent and unreliable. However, when independent sensors agree on similar steep slopes, the signal becomes increasingly difficult to dismiss. Something genuine is occurring. The critical question is whether that something resides within the object itself or within the measurement process. A comparison with canonical comets starkly highlights the anomaly. Typical Oort cloud comets adhere to power laws between -3 and -5, encompassing Halley-type comets, Jupiter family comets, and long-period comets. A few comets have displayed steeper brightening during outbursts or fragmentation events, but these are transient spikes, not sustained trends. 3I Atlas maintained its steep slope across multiple days and several instruments, indicating sustained behavior that demands an explanation, not a fleeting outburst. The temporal evolution adds another layer of complexity. Initial tracking data indicated more moderate brightening, consistent with a power law around -2 or -3. Then, within days or even hours of perihelion, the slope dramatically steepened. This transition was not gradual, it was abrupt. At one moment, the object behaved like a typical, albeit somewhat active, comet. The next moment, it had transformed into something entirely different. While the precise timing remains subject to uncertainty in the current data, it is clear that the steepening occurred during the final approach, compressed into a narrow window around the closest solar distance. Plausible mechanisms for such a steep brightening do exist in theory. One such mechanism involves pressure-cooked volatile releases. Imagine a comet with a thick insulating crust that suddenly fractures under thermal stress, exposing underlying volatile-rich material. This sudden exposure triggers rapid sublimation, inundating the coma with gas and dust, resulting in a spike in brightness. Explosive fragmentation is another potential cause. When a comet nucleus breaks apart into multiple pieces, its surface area increases instantaneously, releasing trapped volatiles and causing a surge in brightness. Furthermore, fluorescent transitions in certain molecules can amplify emission if solar ultraviolet radiation energizes atoms into excited states that then efficiently radiate visible light. However, herein lies the challenge. Pressure-cooked releases and fragmentation typically generate brightness spikes that diminish rapidly, within hours to days, not sustained steep slopes observed over multiple days. Fluorescence depends on the presence of specific molecular species in vast quantities and precise ultraviolet flux conditions, requiring a very particular chemistry and proximity to the sun. These scenarios are possible, yes, but are they probable for an interstellar visitor with an unknown composition? That remains the gamble. Alternative, non-physical explanations must also be rigorously considered. Data artifacts are always a possibility. Saturation effects occur when an instrument's detector pixels reach their maximum capacity, clipping the signal and rendering brightness measurements unreliable. Background subtraction errors arise when the brightness of the surrounding corona is misestimated, leading to the accidental subtraction of too little or too much from the object's signal, artificially inflating or deflating the measurement. Cosmic ray impacts can mimic point sources, although these typically appear in single frames and do not persist across temporal sequences. Investigators must systematically rule out these alternative explanations. They meticulously examine raw frames for signs of saturation. They verify temporal coherence to determine if brightness tracks smoothly or jumps erratically. They compare background readings from different instruments and confirm the consistency of subtraction methodologies. This is painstaking work, and it takes time until this comprehensive analysis is completed and published. Every numerical value currently carries an asterisk. The luminous envelope's spectral data offers a vital cross-reference. The observed interplay between an object's size and its luminescence predictably shifts. If an increase in radiance was solely attributable to the coma scattering more solar light, one would anticipate a proportional expansion of the envelope's dimensions. The surface brightness per pixel should remain largely consistent. However, should the enhanced radiance stem from the object generating its own light rather than merely reflecting it, the surface brightness per pixel could escalate even if the envelope's size remained stable or enlarged at a slower pace. The observation from the GU-19 instrument points towards emitted light, not just reflection, given that the envelope's surface brightness exceeded expectations for pure scattering. Numerical data is inherently truthful, but its interpretation can be flawed. Decimal points can be misplaced. Units may be incorrectly applied. Calibration constants might be outdated. Every astronomer has tales of groundbreaking discoveries that dissolved under rigorous examination. Some were traced to equipment malfunctions. Others stemmed from computational errors. A few involved genuine signals that were misinterpreted. The annals of astronomy are replete with cautionary narratives about premature conclusions drawn before thorough data validation. This underscores the paramount importance of subsequent analyses. Independent research groups will reevaluate the identical data sets. They will seek access to the raw observational frames. They will deploy their own data processing routines for photometry. They will compare their findings, and within a few weeks, or possibly a few months, a collective understanding will coalesce. Either the pronounced inclination is a genuine phenomenon necessitating novel physical explanations, or it is an artifact requiring improved calibration. At this juncture, we exist in a transitional phase between revelation and substantiation, where every presupposition is tentative and every assertion is accompanied by a caveat. Nevertheless, the object's coloration is a more formidable characteristic to dismiss, and it is to this aspect that our attention now turns. The designation "bluer than the sun" conveys a precise meaning, one that cannot be readily explained away through background noise reduction or oversaturation excuses. Color is inherently a ratio. It possesses self-calibrating properties that absolute brightness lacks. When three distinct instruments concurrently indicate a blue hue, it signifies a genuine spectral signature. Spectral signatures, in turn, provide insights into physical mechanisms, revealing what is luminous and the reasons behind it. This is the pivotal element for unraveling this enigma. Section 4. Color shift. Bluer than the sun. Three words that ordinarily do not apply to a comet. The sun's visible light spectrum reaches its peak intensity in the yellow region, approximately 570 nanometers, with a gradual distribution extending to shorter and longer wavelengths. We perceive this as white light, though it is in reality a composite. When sunlight is dispersed through a prism, the familiar spectrum of colors emerges. The sun's luminosity curve demonstrates a dominance of yellow-green wavelengths. Objects that reflect solar radiation should ideally exhibit spectra mirroring that of the sun. A neutral color, such as gray dust or white ice, represents the typical baseline. Blue coloration indicates a proportionally higher emission at shorter visible wavelengths, more violet, deeper blues, and less yellow and red. For an object to register as bluer than the sun, its spectrum must exhibit a bias towards shorter wavelengths relative to the solar reference. This bias necessitates a specific mechanism. Either the object scatters light in a manner that favors blue wavelengths, or it emits light that produces blue hues, or a combination of both. Color photometry using a coronagraph operates by capturing images through distinct optical filters. One filter permits the passage of blue light, approximately at 450 nanometers, while another allows red light, around 650 nanometers, to pass. The brightness within each filter's passband is measured. The ratio of these brightnesses is then computed and compared to the sun's ratio under identical filter conditions. If the object's blue to red ratio surpasses that of the sun, the object is deemed bluer. Conversely, if it is lower, it is considered redder. The principle is straightforward, but practical application is complex due to the finite bandwidths of filters, the wavelength-dependent sensitivity of detectors, and variations in background light across the observational field. The observed deviation in the case of Comet 3I 2019 Y4, Atlas, was not negligible. It was not a mere statistical fluctuation of one standard deviation. It represented a significant shift measured in multiple standard deviations. The computed color indices definitively placed the object on the bluer side of the solar spectrum, and critically, multiple instruments concurred. The Stereo A, SOHO, and GOES 19 spacecraft, employing different filter sets and calibration procedures, arrived at the same conclusion. Such convergence is difficult to attribute to a simple artifact. Potential physical explanations for blue emission within the context of a comet can be broadly categorized into three main groups. Firstly, gas emission lines or molecular bands. Certain molecular compounds emit light strongly at specific wavelengths when energized by solar ultraviolet radiation. Cyanogen, CN, emits around 380 nanometers in the near ultraviolet to violet range. Diatomic carbon, C2, exhibits bands in the blue and green portions of the spectrum. These emissions can impart a greenish or bluish tint to comets when these molecules are the dominant constituents of the coma. It is common for comets to appear slightly green in images due to C2 and CN emissions. However, the reported blue hue of 3I Atlas is described as more intense and spread over a wider envelope than typical cometary green coloration. The second mechanism involves scattering by extremely small dust particles, measuring less than 1 micron in size. Rayleigh scattering, the same physical principle responsible for the blue color of Earth's sky, favors shorter wavelengths. If the dust particles within 3I Atlas's coma are exceedingly small, smaller than the wavelength of visible light, they will scatter blue light more efficiently than red light, resulting in a blue-tinted coma, even if the dust itself is intrinsically dark or neutral in bulk. The challenge lies in the fact that scattering requires specific grain sizes and a substantial quantity of fine particles. Cometary dust typically consists of particles too large to produce pronounced scattering effects, which is why most cometary comas appear neutral or slightly reddish rather than blue. The third mechanism pertains to plasma processes. Electron impact excitation occurs when high-energy electrons collide with atoms or molecules, elevating them to excited states from which they subsequently emit visible light. Solar wind electrons could drive such processes in close proximity to the Sun. Certain emission lines, such as the forbidden oxygen lines around 500 nanometers or the hydrogen Balmer lines, could contribute to visible blue or blue-green emission. Plasma fluorescence within a dense coma subjected to intense solar ultraviolet radiation might generate blue light, provided the appropriate ions and excitation conditions are present. Known cometary emissions include CN and C2, as previously mentioned, which are responsible for the characteristic green color of comets. However, 3I Atlas presents a divergence. The magnitude of the effect is significant. If CN and C2 alone were the cause, extraordinarily high production rates would be necessary to account for the observed brightness. Furthermore, the extensive spatial distribution of the blue envelope suggests a more pervasive phenomenon than localized molecular bands. The coronagraph observation revealed the blue color extending across an envelope spanning 300,000 kilometers, an immense distance. CN emission typically predominates in the inner coma, within 10,000 to 50,000 kilometers of the nucleus. Extending blue emission to 300,000 kilometers implies either an immense production rate or an alternative emission mechanism. The critical question thus becomes distinguishing between emission and reflection. Sunlight reflected by dust generates a spectrum that mirrors the sun's, resulting in a neutral color. An object emitting its own light produces a spectrum determined by the emission mechanism, whether through atomic emission lines, molecular fluorescence, or thermal radiation, each possessing a characteristic spectral profile. The coronagraph observation by the GO-ES spacecraft suggests emission because the brightness and color do not scale in a manner consistent with pure reflection. Reflected light should diminish rapidly as the envelope expands, while conserving total luminosity. Emitted light can maintain its brightness if the emission process is continuously energized by solar flux. The presence of supervolatiles offers a potential link. Carbon monoxide, CO, and carbon dioxide, CO2, exhibit emission features and fluorescent pathways. The SPHEREX mission reportedly detected CO2 in 3I Atlas's spectrum as early as August, considerably before its perihelion passage. This detection established the object as being rich in volatile compounds. CO2 ice sublimates at approximately 150 Kelvin, a temperature considerably lower than that required for water ice. If 3I Atlas contained a substantial amount of CO2, it could be outgassing vigorously in proximity to the Sun, seeding the coma with molecules that subsequently fluoresce under ultraviolet excitation. Some CO2 emission bands fall within the blue to ultraviolet range. A coma driven by copious amounts of CO2 could, in theory, produce extended blue emission, but caution is warranted. Instrument calibration and scattered sunlight can falsely indicate bluer measurements, even when the object's true spectrum is neutral. Coronagraphs are optimized for observing the solar corona, not faint celestial objects. Color indices derived from coronagraph data carry greater uncertainties than those obtained from dedicated photometric instruments. Stray light scattered within the instrument might preferentially impact one filter over another, thereby skewing the color ratio. Vignetting could enhance the blue filter's sensitivity near the field center, where the object happened to be positioned, artificially amplifying the blue signal. Nevertheless, corroboration across multiple sensors diminishes the likelihood of a purely instrumental artifact. If Stereo A's blue measurement was solely due to stray light, why did SOHO and GOES also detect blue? If it were caused by vignetting, why did it persist across multiple frames as the object traversed the field of view? Explanations based on artifacts must account for such consistency. Anomalies within a single instrument are readily explained. Consistency across multiple instruments, however, presents a significant challenge. The paper itself offers a telling statement. The reason remains unclear. Experienced astronomers do not make such pronouncements lightly. They do so when their theoretical models fail to align with observations, when readily apparent explanations prove inadequate, and when the data point towards an uncomfortable reality. Avi Loeb has cultivated a reputation for pushing scientific boundaries and posing challenging questions. His team's candid admission of uncertainty is both honest and unsettling. It leaves open the possibility of exotic natural chemistry, instrumental misinterpretations, or something even more extraordinary. Whatever generated that blue luminescence, the observed pattern suggests processes operating at scales and intensities not typically observed in comets. This could be natural chemistry pushed to an extreme, with volatiles outgassing with unprecedented vigor from an interstellar visitor possessing an unusual composition, or it could be something entirely different, something that deviates from the established cometary paradigm altogether. It compels us to consider possibilities beyond the familiar catalog of solar system objects. And this leads us to the hypotheses, the competing theoretical frameworks, the explanations that span the spectrum from the mundane to the paradigm-altering. Let us articulate them plainly and ascertain which one withstands scrutiny against the empirical data. Part 5. Implications and immediate hypotheses. Three distinct categories of hypotheses, three potential explanations for the phenomenon we are observing. Each carries specific predictive consequences and offers avenues for empirical testing. Let us clearly delineate our assertions from our speculations. Hypothesis A posits a naturally occurring supervolatile comet. This serves as the baseline, the null hypothesis, an explanation that necessitates the least disruption to existing scientific theory. 3I Atlas is presumed to have formed in another star system, possessing a composition distinct from that of solar system comets. It might exhibit a higher refractory content or be richer in carbon monoxide, carbon dioxide, or molecular oxygen. It likely spent millennia traversing interstellar space, remaining cold and inert before entering our solar system. As it approached the Sun, intense solar heating triggered vigorous outgassing of supervolatile ices that sublimate at low temperatures. The rapid brightening observed is interpreted as a consequence of explosive sublimation. The blue coloration is attributed to molecular emissions from species such as CN, C2, oxygen lines, or CO2 fluorescence, which populate the coma with blue-emitting constituents. The expansive luminous envelope is viewed as an immense gas cloud energized by solar ultraviolet radiation, radiating across hundreds of thousands of kilometers. The earlier detection of CO2 by Spherex in August provides support for this hypothesis, indicating the object's volatile content was present months prior to perihelion. If CO2 ice was abundant and subsequently underwent rapid heating near perihelion, a surge in outgassing would be expected. Models suggest that supervolatile ices can produce steep brightness curves under specific conditions. While not reaching the extreme steepness of -7.5 observed in most simulations, they can result in brightness increases steeper than those seen in water-dominated comets. It is conceivable that 3I Atlas simply pushed the boundaries of volatile-driven brightening to an unprecedented extreme, owing to its interstellar origin and potentially unfamiliar composition. Expected observational signatures supporting this hypothesis include the detection of specific emission lines in the visible and infrared portions of the spectrum. Carbon monoxide possesses strong infrared bands around 4.7 microns. Carbon dioxide exhibits bands around 4.3 microns and 15 microns. Cyanogen has emission lines in the ultraviolet to violet range. Diatomic carbon features green emission lines. If hypothesis A holds true, observations by the Hubble and James Webb space telescopes in December should reveal these lines when observing 3I Atlas. The resulting spectrum should resemble that of a gas cloud rather than a reflection spectrum. The ratio of gas to dust should be high. The object should exhibit significant non-gravitational acceleration as the outgassing exerts a propulsive force, deviating the nucleus from its purely gravitational trajectory. Hypothesis B proposes an exotic physical process. This hypothesis maintains the object's natural origin but invokes less common mechanisms. These include plasma fluorescence driven by solar wind electrons, which excite atoms and ions to high-energy states that then emit visible light. Another possibility is dust grain charging, leading to luminescence as charged particles interact with grain surfaces. Magnetic field interactions are also considered. If the object somehow retained a remnant magnetic field from its formation environment, its interaction with the solar wind could generate emissions. These scenarios are speculative but not entirely impossible. We have observed plasma processes responsible for auroras on planets and luminescence within planetary magnetospheres, as well as X-ray emissions from comets, resulting from collisions between solar wind ions and cometary gas. The challenge lies in the scale of these phenomena. Auroras on Earth are bright but localized. Cometary X-ray emissions are faint, requiring sensitive detectors. To produce visible light intense enough to appear bluer than the sun in coronagraph photometry would necessitate significant energy deposition. Solar wind electron fluxes near the sun are indeed high. However, efficiently converting this energy into visible emission requires specific conditions, such as high gas density to facilitate electron collisions with the appropriate atomic and molecular species possessing accessible excited states, and specific geometries that enhance emission, like bow shocks or magnetic cusps that focus electrons. Predicted observational signatures for hypothesis B include ion emission lines, indicative of ionized oxygen, carbon, and nitrogen, as well as non-thermal emission that deviates from blackbody curves. Polarization patterns consistent with scattering in a magnetized plasma would also be expected, along with variability tied to solar wind conditions, given that electron fluxes fluctuate with solar activity. Rapid temporal changes would occur as plasma processes respond to solar wind fluctuations more swiftly than thermal processes react to heating. Hypothesis C, engineered activation, represents the speculative extreme, the unsettling what-if scenario. This hypothesis provokes unease among mainstream astronomers, but cannot be dismissed without compelling evidence. If 3I Atlas were a fragment of manufactured material designed to withstand stellar encounters, it might incorporate refractory alloys that resist sublimation or coatings that fluoresce under intense ultraviolet radiation or heat. It could possess mechanisms that activate only when specific energy thresholds are met, such as solar flux exceeding a triggering level. The rapid brightening and blue emission could then be interpreted as deliberate responses programmed into the material's structure. The rationale behind such a design remains highly speculative. Perhaps it serves as a probe or debris from a long-extinct civilization's construction project, or even a signaling device intended to announce its presence when bathed in starlight. Alternatively, it might simply be wreckage, an unintended activation of systems never intended to operate in this manner. None of this constitutes evidence. It is a thought experiment. However, thought experiments are crucial scientific tools for exploring the parameter space of possibilities before empirical data narrows down the options. Observational signatures for hypothesis C are challenging to pinpoint. If engineered, the object might exhibit structural regularity in high-resolution imaging, such as geometric shapes, symmetries, or non-random fragmentation patterns if it were to break apart. Spectra could reveal materials with unusual compositions, with refractory elements present in ratios inconsistent with natural formation pathways. Narrow band emission lines that do not correspond to known atomic or molecular transitions might hint at artificial phosphors or engineered emitters. Telemetry, such as periodic signals, would serve as definitive proof, but this is considered highly improbable. No one seriously anticipates 3I Atlas broadcasting. For each hypothesis, follow-up observations will provide decisive tests. Spectroscopy is the key. High-resolution spectra across the visible, ultraviolet, and infrared ranges will clarify whether the blue light originates from CN and C2 gas emissions, hypothesis A, or from a more exotic source. Polarimetric imaging will constrain dust properties and magnetic field orientations. High-cadence imaging will track rapid structural changes or variability patterns. Radar, if geometrical conditions permit, could probe for dense, solid structures inconsistent with a rubble pile cometary nucleus. Risk assessment is also relevant. If hypothesis C were true, and we were dealing with an engineered object, what would be the implications? In all likelihood, there would be no immediate threat. 3I Atlas is not on a collision course with Earth. Its closest approach is projected for December 19th, at a distance of 0.93 astronomical units, still well beyond Earth's orbit. Even if it were deliberately constructed, this does not imply hostile intent. It could be passive, inert, a relic. The scientific and philosophical ramifications would be profound, but the practical dangers minimal, offering reassurance without outright dismissal. Historical parallels can help frame this situation. I-2017 U-1, Oumuamua, the first confirmed interstellar object, exhibited non-gravitational acceleration without visible outgassing. This was perplexing, and models struggled to explain it. Avi Loeb proposed a solar sail mechanism, an engineered light sail propelled by radiation pressure. Mainstream scientists favored explanations involving exotic ice sublimation, such as hydrogen or nitrogen icebergs. Neither explanation was entirely satisfactory. 2I 2019 Q4, Borisov, the second interstellar visitor, behaved like a conventional comet, displaying familiar chemistry, fragmentation, and outgassing, presenting no surprises. 3I Atlas might represent a third category, distinct from Oumuamua's apparent inertness and Borisov's conventional behavior, thus defining a new class of object. Interstellar visitors have consistently surprised us. Each one has imparted new knowledge. Oumuamua demonstrated that tumbling, elongated objects can traverse interstellar space and that not all comets exhibit visible outgassing. Borisov confirmed that some interstellar comets closely resemble our own, validating the universality of cometary processes. 3I Atlas, whatever its nature, is teaching us that the frontier of discovery still holds mysteries, that our models are provisional, and that nature, or something else entirely, can still deliver unexpected revelations. The question of data quality looms large. Is this a genuine physical mystery, or a mirage created by the measurements? This is the central focus of the subsequent analysis. We will meticulously examine the instruments, scrutinize the calibrations, confront skeptical viewpoints, and map the competing theoretical camps. We will delve into other observed anomalies, such as the growth of the anti-tail, the orbital residuals, and the apparent absence of early flares. We will either reconcile these apparent contradictions or expose them as irreconcilable. By the conclusion of this investigation, it will be clear whether 3I Atlas is fundamentally altering our understanding of comets or merely testing our patience. The enigma deepens. The instruments have made their pronouncements. Now it is imperative to listen more intently. Part 6. Reconciliation with other anomalies. 3I Atlas did not confine its surprises to its perihelion passage. The object has been presenting anomalies for months, and not all of these fit neatly into a singular narrative. Allow me to enumerate the other observed phenomena. An anti-tail reportedly increased in length from 600 to 720 kilometers within a 24-hour period. Orbital residuals indicate minute gravitational influences from Earth. Astrometric positions deviate from purely gravitational predictions by fractions of an arcsecond. Earlier reports suggested minimal perihelion flare activity in some datasets, directly contradicting the explosive brightening captured by the coronagraphs. These are not trivial details. They represent fragments of a puzzle that may not originate from the same box. The timeline of events is significant. Weeks to months prior to perihelion, ground-based telescopes tracked 3I Atlas as it approached the Sun. These observations indicated moderate activity, with some dust production, nothing particularly alarming. Subsequently, in August, the SphereX mission detected carbon dioxide, confirming the object's volatile content. This was followed by the perihelion passage in late October and the subsequent coronagraphic observations, which revealed spectacular activity. We are now in the early days of November, awaiting the celestial body's reappearance from the Sun's blinding glare, which will allow Earth-based observatories to resume their tracking efforts. Different instruments capture distinct time frames. Various phenomena are observed at different moments. Are these discrepancies or complementary findings? Three potential explanations emerge. The first scenario posits that diverse instruments were observing distinct phenomena. Coronagraphs register luminance and color. Terrestrial telescopes analyze dust and tail characteristics. Astrometric measurements pinpoint location. Each method examines a unique facet of the same entity, and these facets are not obligated to behave in lockstep. A comet might experience a sudden surge in brightness while its dusty tail remains consistent. Gaseous emissions could dominate the light output even if dust production remains moderate. There is no universal law dictating that all observable traits must fluctuate in unison. The second scenario suggests the object underwent a sudden behavioral shift around its closest approach to the Sun. It is conceivable that 3I 2019 Q4 was relatively quiescent for several months. Subsequently, something may have been triggered at a close solar proximity. This could involve thermal stress fracturing the surface, pressure buildup releasing abruptly, or a phase transition within subsurface ice. If we entertain the engineered hypothesis, it might represent an activation threshold. Celestial bodies can undergo transformations in their state. Comets can fracture, asteroids can crack. If 3I 2019 Q4 transitioned from one state to another, early observations and those made near perihelion would appear contradictory, even though both are accurate snapshots of different phases. The third scenario proposes that some earlier observations were misinterpreted. Photometry is challenging. Tail estimations are difficult. Astrometry is exceptionally demanding when dealing with faint, diffuse objects near the Sun. It is possible that the reported minimal early flare was, in fact, a measurement error. The object may have been lost in background noise or mistaken for stars. Perhaps the growth of the anti-tail was an optical illusion stemming from the viewing geometry rather than a genuine ejection of mass. It's also conceivable that orbital discrepancies were statistical anomalies, noise masquerading as a meaningful signal. Misinterpretation does not equate to incompetence. It signifies operating at the limits of instrumental capabilities, where errors are readily made and confirmation is a protracted process. Let us specifically examine the expansion of the anti-tail. An anti-tail is an optical illusion. Dust particles ejected from a comet do not travel in a straight line away from the Sun. Instead, they follow slightly curved trajectories, trailing behind the nucleus. When Earth's vantage point aligns correctly, we perceive these trailing particles projected against the sky in a manner that suggests a tail pointing towards the Sun. This is an anti-tail. It is a matter of geometry, not physics. The particles are not actually moving sunward. We are simply viewing them from an angle that creates this illusion. The reported expansion from 600 to 720 kilometers within 24 hours indicates either a change in the dust distribution or a shift in our viewing angle. The viewing geometry alters gradually over days as Earth and the comet progress in their orbits. An apparent change of 120 kilometers in a single day is more rapid than geometry alone would predict, hinting at actual dust dynamics. It is possible that fresh dust was expelled in a sudden burst, populating the anti-tail region. Alternatively, existing dust may have been accelerated by solar radiation pressure, expanding the tail spatially. In either case, anti-tail behavior is intrinsically linked to dust. The perihelion brightening, however, pertains to gas emission and potentially small particles of dust. These phenomena could coexist without conflict. Orbital discrepancies are more perplexing. Astrometry ascertains an object's apparent position in the sky. Ephemerides predict its expected location based solely on gravitational forces. Residuals represent the differences between these two. Positive residuals directed towards Earth imply the object is slightly closer to Earth or marginally ahead in its orbital path compared to predictions. The reported values, starting at plus 0.37 arcseconds and increasing to plus 0.43 arcseconds, are minute, representing a fraction of a pixel in most telescope images. Measuring these requires precise calibration and meticulous elimination of systematic errors. What triggers non-gravitational residuals? Outgassing jets generate thrust. A comet venting gas predominantly in one direction experiences a propulsive effect, a minuscule push that accumulates over time. Radiation pressure from sunlight propels lightweight dust particles. Furthermore, if the comet sheds dust asymmetrically, the nucleus can recoil. Microthrusts resulting from mass loss, even if the mass loss is symmetric, can produce net forces if the nucleus is rotating. And jets can activate and deactivate in sync with rotation. All these mechanisms are well understood. We routinely observe them in solar system comets. The challenge lies in correlating residuals with brightening. If 3I 2019 Q4 experienced violent mass ejection at perihelion, resulting in the steep brightness curve, one would anticipate substantial non-gravitational acceleration. Gas jetting at high velocity carries momentum. Mass loss alters the orbit, yet the reported residuals are small, subtle, and perhaps not even statistically significant given measurement uncertainties. This is peculiar. Explosive outgassing should generate detectable thrust. If it does not, it implies either that the outgassing was largely isotropic, meaning forces canceled out, or that the brightening was not attributable to mass ejection at all. Here is a potential reconciliation. Let us assume the blue emission originated from gas fluorescence rather than from scattering off newly ejected dust. Gas molecules absorb solar ultraviolet radiation, enter excited states, emit visible light, and then return to their ground states. This process radiates light, but does not necessitate mass loss in the sense of material permanently departing the nucleus. The gas can expand, emit, and then be ionized or dissociated by the solar wind without imparting a net thrust on the nucleus. If the expansion is symmetric, brightness would be observed without acceleration. Alternatively, if the brightening involved emission from a reflective or fluorescent surface rather than mass ejection, one would indeed observe brightness without thrust. Engineered materials that luminesce under ultraviolet light would not shed mass. They would simply radiate. This aligns with hypothesis C, but requires acceptance of the engineered premise, which remains speculative. In contrast, Oumuamua, the interstellar object I-2017 U1, displayed measurable non-gravitational acceleration without a visible coma or tail, indicating no dust or gas. The acceleration was real, verified by multiple observatories, statistically significant, yet no signs of outgassing were detected. Explanations ranged from the sublimation of invisible hydrogen icebergs to solar sails capturing radiation pressure. The tension between acceleration and the absence of visible activity defined the Oumuamua mystery. 3I 2019 Q4 might present the inverse tension: visible activity, dramatic brightening, but minimal acceleration. This is the opposite of Oumuamua. 2I Borisov, another interstellar visitor, behaved conventionally. Its brightening correlated with outgassing, its non-gravitational forces matched visible dust and gas production, and fragmentation events corresponded to brightness changes. Everything made sense. Borisov was normal. Its peculiarity was in one direction. 3I 2019 Q4 might be peculiar in a different direction, with each interstellar visitor establishing its own category within the taxonomy of strange objects. Reasons for discrepancies abound. Spatial resolution varies dramatically among instruments. Ground-based telescopes resolve the nucleus and inner coma. Coronagraphs observe extended envelopes but blur fine details. Different spatial scales capture different physical processes. Spectral sensitivity is also crucial. Instruments operating in visible light may miss infrared emissions. Ultraviolet instruments may fail to detect red light. An object emitting brightly in one wavelength range might appear faint in another. Observation geometry fundamentally alters perception. The angle between the sun, the object, and the observer determines which dust features are discernible, which gas emissions exhibit Doppler shifts, and how tails are projected against the sky. Reconciling these contradictions necessitates that instrument teams publish detailed calibrations, observation logs, and processing methodologies. Independent analysts require access to raw data. Comparisons must account for varying sensitivities, differing observation times, and distinct fields of view. This is a laborious process, taking weeks to months. Peer review requires time but is indispensable. Hasty conclusions regarding anomalies tend to dissipate upon closer scrutiny. The lingering question is whether 3I 2019 Q4 is genuinely anomalous or simply perplexing. Anomalous implies that the physics does not align. Perplexing suggests that the observations do not yet align because they have not been fully understood. History offers examples of both. Pulsars were considered anomalous until neutron stars were discovered. Fast radio bursts were perplexing until improved localization and identification of host galaxies were achieved. Some mysteries resolve into new physics, others resolve into enhanced measurements. Where does 3I 2019 Q4 fit? We will not know until the instruments are rigorously examined, the calibrations are verified, and the observation campaign continues through December. The subsequent step involves confronting skeptics and scrutinizing the calibration risks that could cause this entire drama to dissolve into instrumental artifacts. Because if the coronagraphs were mistaken, if the brightness curve and color shift were illusions born of stray light and flawed background subtraction, then we are pursuing phantoms. And we must ascertain this fact before we revise textbooks or proclaim a paradigm shift. Skepticism is not obstruction, it is due diligence. Let us hear the doubters' perspectives. Part 7. Instrument Team Skepticism and Calibration Risks. Professional caution is not cowardice, it is a survival mechanism. Mission teams operating stereo, SOHO, and GOES did not construct billion-dollar spacecraft to hastily assert findings about interstellar comets. Their objective was to study the sun, monitor space weather, and track coronal mass ejections. When an unusual signal appears in their data, their initial inclination is not to publish but to verify, double-check, and triple-check. They ensure the signal is authentic before associating their names and their mission's reputation with a claim that could prove incorrect. This represents sound scientific practice, safeguarding against embarrassment and preserving credibility over decades. Coronagraph teams have encountered numerous peculiar signals over the years. These include dust grains impacting detectors, cosmic rays traversing frames, electronic glitches generating phantom images, and stray light from planets, bright stars, or internal reflections. Most anomalies are mundane once thoroughly investigated. The true difficulty lies in distinguishing the single genuine signal from the 99 false positives. Calibration issues for coronagraphs are numerous and technical. Stray light poses a persistent challenge. Sunlight scatters internally within the instrument, reflecting off baffles, diffracting around edges, and bouncing off optical surfaces. Even with meticulous design, a fraction of solar photons can end up in unintended locations, contaminating the image. Stray light patterns are complex, varying with the sun's position relative to the instrument, the spacecraft's orientation, and thermal conditions affecting optical alignment. Correcting for stray light requires intricate models derived from years of in-flight calibration data. Vignetting alters color ratios across the field of view. The detector's sensitivity is not uniform. Edges are less sensitive than the center. Different filters exhibit distinct vignetting due to variations in lens coatings and detector quantum efficiency with wavelength. An object at the frame's edge might appear artificially red or blue compared to one at the center, not due to genuine color differences but to instrumental response. Flat fielding corrects for this by imaging uniform sources and dividing science frames by the flat field. However, flats are never perfect. Pixel nonlinearity causes bright sources to deviate from proportional scaling. Detectors are designed to respond linearly to light. Double the photons should yield double the signal. Yet, at high or low signal levels, detectors diverge from linearity. Bright objects saturate, clipping the signal at the maximum pixel value. Faint objects approach noise floors where red noise and dark current dominate. Nonlinearity curves must be measured and corrected, and these corrections introduce uncertainties. Saturation is particularly problematic. Once pixels reach their maximum value, information is irretrievably lost. The true brightness cannot be recovered. One can attempt to estimate it by fitting the wings of the point spread function using nearby unsaturated pixels to infer the central brightness, but this method is model-dependent and prone to error. If 3I-2019Q4 saturated the detector during perihelion, brightness measurements become estimations rather than empirical data. Cosmic ray impacts can be mistaken for genuine sources. High-energy particles from space strike the detector, depositing charge that resembles a bright spot or streak. Single-frame cosmic rays are easily rejected by comparing consecutive frames. If a bright spot appears in one frame but not the next, it is likely a cosmic ray. However, if cosmic rays strike the same region repeatedly by chance, or if the object being tracked coincidentally overlaps with cosmic ray impacts, confusion can arise. Sunlight scattering within the optics generates artifacts that can resemble extended sources, such as diffraction spikes, lens flares, and ghost reflections. Coronagraphs minimize these through careful baffle design and multiple occulting disks, but cannot eliminate them entirely. A bright star just outside the field of view can scatter light that manifests as a faint halo within the image. The sun's own diffraction pattern, even when its disk is occulted, produces faint rings and spokes. Distinguishing a genuine cometary coma from a scattering artifact requires experience and often multi-epoch observations to confirm that the source moves with the expected cometary trajectory. Science teams mitigate these issues using standard techniques. Flat fielding corrects vignetting. Dark frame subtraction removes detector bias and thermal noise. Cosmic ray rejection algorithms cleanse single-frame impacts. Background modeling subtracts the average corona, leaving the moving object. Temporal coherence checks verify that brightness tracks smoothly over time. Cross-comparisons between multiple instruments identify systematic errors affecting one sensor but not others. The significance of cross-confirmation between independent instruments cannot be overstated. Stereo A, SOHO, and GOES 19 possess different optical designs, detectors, and orbital positions. An artifact impacting one should not affect all three in the same manner. If all three report a steep brightness curve and a blue color, it would necessitate a conspiracy of errors. Stray light contaminating stereo's blue filter, vignetting biasing SOHO's color measurement, and background subtraction failing identically on GOES are all conceivable but improbable. Each additional confirmation renders the artifact hypothesis less tenable. However, critics might contend that coronagraph color indices are unreliable for faint moving objects. They may argue that coronagraphs are optimized for extended coronal structures, not point sources, and that photometric measurements of small comets are at the limits of capability. Furthermore, they might assert that converting detector counts to calibrated flux involves assumptions about spectral shape, which break down if the object's spectrum is unusual. These are all valid points, worthy of investigation. Historical precedents exist for coronagraph misinterpretations. SOHO's LASCO instrument once detected features initially believed to be interesting coronal structures, but later identified as dust grains on the detector's faceplate. Bright comets passing through the field have occasionally produced artifacts resembling secondary tails or companion objects, subsequently explained as optical ghosts. Modern teams are more adept at identifying these due to lessons learned from past mistakes. Nevertheless, perfection remains an elusive goal. The procedural steps the scientific community will undertake are currently unfolding. Private instrument team reviews are in progress. Experts at the Naval Research Laboratory, which operates LASCO, and at the Stereo and GOES teams are examining raw frames, verifying calibration files, and conducting independent photometry. Papers detailing calibrated flux conversions and comprehensive error analyses are being prepared. Community replication will follow once the data are publicly released. Amateur astronomers and professional skeptics will download the frames and perform their own analyses. Consensus will emerge from this process, not from a single team's assertion. Expected timelines involve weeks for preliminary checks and months for full peer-reviewed publication. Science progresses more slowly than social media platforms. Hype cycles demand immediate answers, while science requires patience. The tension between public curiosity and scientific rigor breeds frustration. People desire immediate answers. Is it real or not? Is it extraterrestrial or not? Science responds, "We are working on it. Check back in February when the papers are published and vetted." Headlines will likely be divided between controversial and confirmed, depending on the source. Avi Loeb's advocacy for considering the engineered hypothesis makes him a polarizing figure. Supporters commend his willingness to explore unconventional ideas. Critics accuse him of seeking publicity, of jumping to conclusions, and of fostering false hope among UFO enthusiasts. Both viewpoints hold some validity. Loeb has been correct in the past, proposing ideas that were initially dismissed but later validated. He has also been incorrect, making claims that did not withstand scrutiny. Science is not about authority, it is about evidence. The data will ultimately provide the answers, not reputations. So, what would constitute genuine confirmation? What observations would settle the question beyond a reasonable doubt? Confirmation necessitates the convergence of multiple lines of evidence. Spectroscopy revealing anomalous emission lines unexplainable by known cometary chemistry. high-resolution imaging displaying structures inconsistent with a natural rubble pile nucleus, detection of periodic signals or spatial patterns indicative of design, non-gravitational accelerations precisely correlating with brightness changes, thereby proving mass ejection as the cause. Conversely, the absence of acceleration proving emission without mass loss. Independent replication by multiple teams utilizing different instruments, all agreeing on brightness, color, and spectral features. Confirmation also requires the exclusion of alternative explanations, demonstrating that instrumental artifacts cannot account for the signal, showing that calibration errors would need to be implausibly large and correlated, and proving that natural mechanisms, even exotic ones, fail to produce the observed combination of properties. Extraordinary claims demand extraordinary evidence, and extraordinary evidence entails exhausting all ordinary explanations. First, the drama of discerning the real from the fake, signal from noise, discovery from artifact, is central to modern astronomy. Every significant finding undergoes this rigorous testing. Gravitational waves were debated for decades prior to LIGO's detection, and even then, skeptics demanded verification. Exoplanets were controversial until Doppler surveys and transit observations accumulated overwhelming statistical significance. Fast radio bursts were initially suspected to be instrumental glitches until multiple telescopes confirmed their existence. 3I 2019 Q4 is merely the latest object to enter this crucible. It will either emerge validated, representing a genuine anomaly demanding new theoretical models, or it will dissipate, serving as a cautionary tale about making measurements at the limits of capability. We stand at an inflection point. The instruments have provided their data. The teams are conducting their checks. The scientific community is observing, and in the background, December 19th approaches, the date when 3I 2019 Q4 makes its closest approach to Earth, finally offering ground-based telescopes their opportunity. If the coronagraphs were accurate, December will bring confirmation and spectacle. If they were erroneous, December will bring disappointment and lessons learned. Either way, we are on the verge of discovery. The scientific process that resolves such questions is already in motion. Now, let us examine what kind of object could naturally produce these signals and what kind of object would necessitate abandoning natural explanations entirely. Part 80. The Origin Story. Natural versus Engineered. Natural object or engineered artifact. Both are hypotheses. Neither is a definitive conclusion. Let us be explicit about this framing. We are exploring the parameter space, not declaring absolute truth. Science operates by proposing models, deriving predictions, comparing them to observations, and iteratively refining them. Currently, our observations diverge from established models for cometary behavior. Consequently, we must broaden our theoretical framework. This involves considering celestial bodies possessing unusual chemical compositions or physical processes observed in principle but never on such a grand scale. Alternatively, we might be encountering manufactured materials exhibiting properties unattainable through any known natural formation. All three possibilities remain on the table until definitive evidence eliminates one or more. The path of natural origin commences in a distant star system, possibly millions or billions of years ago. Within a protoplanetary disk surrounding a young star, planets, asteroids, and comets coalesce. Certain bodies might form with compositions distinct from those in our own solar system, featuring elevated carbon content, more resilient organic compounds, and atypical inventories of volatile substances. Perhaps the radiation environment of the parent star differed, thereby altering the chemistry of ices. It's also conceivable that massive planets within that system gravitationally scattered objects, preferentially ejecting carbon-rich bodies. While we lack direct knowledge, having never explored the cometary cloud of another star, we understand that chemical variations are linked to stellar metallicity, temperature, and ultraviolet flux, making diversity an expected phenomenon. Ejection occurs through gravitational scattering, where a planet's gravitational pull imparts sufficient velocity to an object, exceeding the star system's escape velocity. The object then embarks on an interstellar journey, traversing space for millennia. This prolonged voyage exposes it to cosmic rays and ultraviolet radiation from the galactic background, alongside occasional close encounters with other stars. Such interactions modify its surface chemistry, processing organic molecules. Even in the frigid vacuum of interstellar space, volatiles might slowly sublimate if exposed to sufficient energetic particles. By the time the object enters our solar system, its journey has inherently altered it. Subsequently, it encounters our Sun. The Sun's gravity captures its trajectory, bending its path into a hyperbolic orbit. As the object approaches perihelion, solar heating intensifies. Its temperature rises, causing volatiles to begin sublimation and the development of a coma and tail, leading to increased brightness. For a typical comet, this progression adheres to well-understood scaling laws. However, the object designated 3I Atlas deviates from this norm. If its composition is unusual, its behavior can be equally so. Plausible chemical scenarios focus on carbon-rich matrices and atypical volatile inventories. Refractory organic compounds, complex carbon molecules that only sublimate at very high temperatures, could constitute the bulk of its composition. Embedded within this matrix might be pockets of carbon monoxide, carbon dioxide, or molecular oxygen, all supervolatiles that sublimate at temperatures below the melting point of water ice. As the object heats up, these supervolatiles would vent first, resulting in gas emission with minimal dust. A high gas-to-dust ratio would translate to significant brightness from fluorescence, but relatively little light scattering from solid particles. The detection of carbon dioxide in August by the Spherex instrument confirms the presence of volatiles. Carbon dioxide ice sublimes at approximately 150 Kelvin, which is considerably colder than the 170 to 200 Kelvin required for water ice sublimation. If 3I Atlas is rich in carbon dioxide ice, it would commence outgassing at a greater distance from the Sun than water-rich comets. Closer to the Sun, carbon dioxide sublimation would accelerate dramatically due to the exponential increase in vapor pressure with temperature. This creates a runaway positive feedback loop. More heat generates more gas, which in turn releases latent heat, further increasing the temperature and producing even more gas. This process could drive steep brightness curves. However, the question remains whether this can account for exponents of 7.5. This is where current models falter. Simulations of comets driven by supervolatiles predict steeper brightness curves than those of water comets, but typically in the range of -5 to -6, not -7.5. It is possible that 3I Atlas reached a threshold where subsurface pressure caused the crust to rupture, triggering a catastrophic release of material. Alternatively, it might have fragmented, instantaneously increasing its surface area. Models incorporating fragmentation can indeed produce very steep brightness spikes. The challenge lies in the fact that fragmentation typically generates visible fragments, noticeable changes in morphology, and dust clouds. Whether evidence for such fragmentation exists in the chronograph images is a question that the specialized analysis teams have yet to fully address in their published findings. Now, let us consider the hypothesis of artificial origin, not as a belief, but as a structured thought experiment. If a civilization intended to dispatch a probe through interstellar space and ensure its survival during close encounters with stars, what design choices would be logical? This would likely involve refractory materials resistant to melting or sublimation, a high strength-to-weight ratio, passive systems requiring no active control, and coatings offering protection against ultraviolet and particle radiation. Furthermore, mechanisms that respond to environmental triggers, such as high radiant flux, by changing state in beneficial ways, might be incorporated. Why would activation under extreme flux be advantageous? Speculation abounds here, but let us entertain it. Perhaps the probe is designed to harvest energy when proximate to a star, storing it for later use. It might instead signal its passage, intentionally emitting light to become visible to any observers. Or the material might simply possess properties that cause it to exhibit blue fluorescence under ultraviolet light as a byproduct of its protective coating, not by deliberate design, but as a consequence. A more speculative angle suggests the object was not intended for stellar visitation at all, but is rather debris, a fragment from a larger structure that disintegrated. Its current activation patterns, therefore, are not as intended because it is no longer part of a larger system that regulated its behavior. Evelyn Loeb and her colleagues, who advocate for the consideration of technosignatures, frame this approach as applying the same scientific methodology used for any hypothesis. List predicted observable phenomena, verify their presence, and subsequently update probability assessments. Lowe's reasoning concerning Oumuamua was that its unusual geometry, high aspect ratio, and non-gravitational acceleration without visible outgassing pointed towards an artificial origin, specifically a light sail. Critics countered that natural explanations, such as hydrogen icebergs or nitrogen ice, were also plausible. Neither viewpoint achieved decisive victory due to insufficient data. Oumuamua departed the solar system before detailed spectroscopy could be obtained. Mainstream scientists rightly emphasize natural explanations first. The overwhelming majority of astronomical phenomena stem from natural causes. Invoking engineered artifacts before exhausting all natural possibilities is premature. Carl Sagan's dictum holds true. Extraordinary claims demand extraordinary evidence. A steep brightness curve and blue emission, while unusual, do not constitute extraordinary evidence for engineering. Rather, they represent puzzling observations warranting further investigation. Tests that could differentiate between hypotheses focus on spectroscopy and morphology. Narrowband, non-thermal emission lines would be highly anomalous. Atoms and molecules emit at specific wavelengths dictated by quantum mechanics. Detecting emission lines that do not correspond to any known element or molecule would indeed signify something genuinely peculiar, strongly favoring engineered materials with artificial phosphor compounds. The observation of structurally regular fragments would likewise be telling. Comets typically fragment chaotically, with nuclei splitting along stress fractures to produce irregular pieces. If 3I Atlas breaks into components exhibiting geometric regularity, such as planes, symmetries, or repeated structures, this would be difficult to explain naturally. Telemetry, in the form of periodic signals, remains the ultimate definitive proof, though it is also exceedingly improbable. No astronomer seriously anticipates 3I Atlas broadcasting radio or optical pulses, as such an event would be so obvious and unambiguous that the question would be settled instantly. However, the absence of telemetry does not inherently prove the object is natural. A defunct probe, a piece of debris, or an object not designed for communication would remain silent. Silence is inherently ambiguous. Philosophical reflection on weighing evidence leads us to Bayesian reasoning. One begins with prior probabilities. How likely is it that Three-Eye Atlas is engineered, given our current understanding of the universe? This considers the rarity of technological civilizations, the vastness of space, and the sheer number of natural objects compared to artificial ones. Most individuals assign a very low prior probability, perhaps 1 in a million or 1 in a billion. This probability is then updated based on incoming evidence. The steep brightness curve and blue emission are indeed unusual, thus slightly increasing the posterior probability of the engineered hypothesis. However, a small multiplier applied to a minuscule prior still results in a minuscule posterior. Overwhelming evidence is required to shift a low prior probability to a high degree of confidence. Occam's razor suggests favoring simpler explanations. Natural chemistry is inherently simpler than engineered artifacts because we know natural chemistry exists and routinely produces comets. We have yet to confirm the existence of an interstellar artifact. Introducing engineering into the hypothesis space multiplies complexity, necessitating assumptions about alien civilizations, their capabilities, and their motivations. Unless natural explanations prove entirely inadequate, Occam's razor directs us toward the natural origin. Nevertheless, Occam's razor is a heuristic, not an immutable law. Sometimes the seemingly simpler explanation is incorrect, and complexity is indeed necessary. Pulsars, for instance, initially appeared simple until their nature as spinning neutron stars was understood, requiring the frameworks of general relativity and nuclear physics for explanation. Simplicity serves as a guide, not a guarantee. The debate surrounding Three-Eye Atlas mirrors the Oumuamua debates in both tone and structure. Proponents of the artificial hypothesis question why a possibility should be disregarded simply because it is uncomfortable. Opponents argue why it should be entertained when natural causes have not yet been definitively ruled out. Both approaches are scientific. Both employ skepticism, albeit directed in different ways. One side is skeptical of conventional models, while the other is skeptical of unconventional claims. Ultimately, the data will serve as the arbiter. Historical context reveals a recurring pattern. When quasars were first discovered, some proposed they were artificial beacons. They were not, but rather supermassive black holes accreting matter. Upon the discovery of pulsars, some jokingly referred to them as little green men, LGM. They were not, but neutron stars. The WOW signal detection led some to believe it was an extraterrestrial transmission. It probably was not, though certainty remains elusive. While most anomalies eventually resolve through natural explanations, not all do, and the only way to ascertain their nature is through diligent investigation. What transpires next will provide more insight than mere speculation. Observations scheduled between December and January will yield high-resolution spectra, polarimetry, imaging, and astrometry from instruments that were not available during perihelion. The Hubble, Webb, Keck, and Very Large Telescope, VLT, among others, can be directed at Three-Eye Atlas once it has moved sufficiently far from the Sun. These observations will either corroborate the findings from coronagraph images or refute them. They will either reveal exotic chemistry or familiar chemistry and either display structure or chaos. We will know soon, and understanding is preferable to conjecture, even when the conjecture is more captivating than the eventual answer. Part 9 focuses on the events occurring after perihelion, encompassing observations and predictions. October 29th marked perihelion, while December 19th is designated as the closest approach. This date is significant because it signifies the moment when 3I Atlas fully emerges from the Sun's glare and enters an observational sweet spot for both ground-based telescopes and space observatories. Between now and then, the object is ascending from the Sun's gravitational well, receding from perihelion, and moving into a geometrical configuration that allows Earth-based instruments a clear line of sight without contending with the Sun's overwhelming brightness. On December 19th, it will be 0.93 astronomical units from Earth. While still outside our orbital path, it will be sufficiently close for detailed spectroscopy and imaging with an angular resolution capable of discerning structure, should any exist. Predictive modeling diverges into two distinct scenarios, each possessing concrete observational signatures. Scenario A posits continued brightening. If the processes that fueled the perihelion flare persist, if supervolatile outgassing continues or intensifies, and if emission mechanisms remain active, then the object's brightness should remain elevated or even increase as it traverses late November and early December. Magnitude estimates are contingent upon the models employed. However, if the negative 7.5 scaling trend extends beyond perihelion, 3I Atlas could reach visual magnitudes observable by amateur telescopes, possibly magnitude 8, or even brighter. This would render it visible in twilight skies for observers with dark viewing locations and adequate equipment. Scenario B anticipates a rapid dimming. Many comets that exhibit explosive brightening near perihelion tend to fade quickly thereafter. Fragmentation events, for instance, produce transient spikes that subside within days, and supervolatile reserves can become depleted. If 3I Atlas exhausts its volatiles or fragments into pieces too small to track, its brightness will decline swiftly. Magnitude estimates for this scenario suggest a drop below magnitude 15 by mid-December, rendering it invisible except to powerful professional instruments. This has occurred with other comets and is not unusual, though it would be a disappointing outcome. A brief, spectacular display followed by darkness, leaving us with coronagraph data and unanswered questions. Which scenario is more probable? No one can say for certain. This is precisely why December is a pivotal month. Observations conducted during the first 2 weeks of December will reveal the trajectory the object follows. If its brightness remains constant or increases, scenario A gains credibility. Conversely, if its brightness plummets, scenario B prevails. Either outcome will provide valuable insights. Sustained brightness would support ongoing volatile outgassing or emission, while a rapid fade would suggest an explosive transient release or fragmentation. Priority observation modes for December will concentrate on spectroscopy and polarimetry. Spectroscopic analysis across visible and infrared wavelengths is considered the gold standard. Spectrographs aboard the Hubble, Webb, Keck, and VLT can precisely resolve individual emission lines. These instruments will search for carbon monoxide lines around 4.7 microns, carbon dioxide bands near 4.3 and 15 microns, cyanogen lines in the violet spectrum, diatomic carbon lines in the green, and forbidden oxygen lines at 500 nanometers. Each identified line will reveal the presence and abundance of specific molecules. A spectrum showing strong carbon monoxide and carbon dioxide signals would validate the supervolatile hypothesis. If, however, lines are detected that do not correspond to any known molecules, this would be profoundly anomalous. Polarimetry provides constraints on dust properties. Light scattered by minute particles becomes polarized, and the degree and angle of polarization are dependent on the particle's size, shape, and composition. If 3I Atlas's coma is filled with submicron grains that produce scattering polarization with minimal dust, the polarization will be low. Comparing polarization measurements at different wavelengths can map the distribution of grain sizes. This is a diagnostic technique that distinguishes gas emission from dust scattering, thereby addressing whether the observed blue color originates from small grains or molecular fluorescence. High-cadence imaging allows for the tracking of rapid structural changes. If the object is fragmenting, its pieces will separate over days, becoming visible as distinct sources in images. If jets or asymmetric features are developing, these will manifest as variations in brightness or directional tails. Time-resolved imaging at intervals ranging from hours to days will generate movies of the coma's evolution, revealing dynamic processes not apparent in single snapshots. Hubble's exceptional angular resolution is ideally suited for this purpose. Webb's infrared sensitivity will enable it to penetrate dust and capture thermal emissions, which trace temperature and volatile sublimation. Radar presents a more speculative possibility. If the geometry is favorable, radio telescopes, such as the successor to Arecibo or Goldstone, could ping 3I Atlas and analyze the returning echoes. Radar can detect dense structures, resolve shape and rotation, and measure surface roughness. A porous cometary nucleus would scatter radar signals weakly, whereas a solid metallic object would scatter them strongly. In principle, radar could differentiate between a rubble pile and a denser object, but this requires the object to be relatively close and bright at radio wavelengths, criteria that 3I Atlas may not fully meet. Nevertheless, the attempt is worthwhile. The question of who will observe and when is subject to scheduling constraints. Time on the Hubble and Webb telescopes is allocated months in advance through proposal processes. However, both observatories reserve directors' discretionary time for targets of opportunity, unexpected transient events that demand immediate follow-up. 3I Atlas certainly qualifies. Directors at both missions could approve DDT proposals in late November, allocating observing time in December for spectroscopy and imaging. Ground-based facilities like Keck, VLT, and Gemini also have DDT programs, and requests are likely already being submitted. Coordination among observing teams will ensure complementary observations, avoiding redundancy and maximizing scientific return. Amateur networks also play a crucial role. The amateur astronomy community has demonstrated considerable adeptness in monitoring comets, detecting outbursts, measuring brightness, and tracking morphology. Networks such as the British Astronomical Association's Comet Section or the American Association of Variable Star Observers organize dedicated campaigns. If 3I Atlas brightens sufficiently, hundreds of amateur observers worldwide could contribute photometry, generating a dense temporal data set that professional telescopes, with their limited observing time, cannot match. This crowdsourcing approach has proven effective. The release timelines for processed data vary depending on the mission and the specific research team. Hubble and Webb data are typically archived and made publicly accessible within months. Ground observatory data are subject to proprietary periods set by each facility, usually lasting 6 months to a year before public release. Preprints may appear on archive sooner, sometimes within weeks of the observations if teams expedite the process. Preliminary results are disseminated even more rapidly through social media, though with a corresponding decrease in reliability. By January, we can expect initial reports. By March, peer-reviewed scientific papers should be available. By mid-2026, the complete dataset will be public and subject to thorough scrutiny by the scientific community. Fourth, fragmentation. If imaging reveals multiple distinct nuclei or expanding debris clouds, this would confirm structural disruption. Fifth, changes in non-gravitational accelerations. If astrometry indicates accelerations that increase in magnitude or shift direction, this would map out gassing patterns and test whether a given trajectory correlates with thrust. This suggests a watch list for the public. In mid-December, observers should direct their attention toward the eastern sky before dawn or the western sky after sunset, depending on 3i Atlas's position. Precise coordinates will be disseminated on astronomy websites and applications such as Stellarium or Sky Safari. Should its brightness reach magnitude 8 or 9, even small telescopes and good binoculars might detect it as a faint, fuzzy patch. Naked eye visibility is unlikely unless its brightness exceeds magnitude 6, which is an optimistic projection. A safety note: never observe near the sun without appropriate filters. An ethics note: refrain from claiming discovery or issuing alerts without confirmation through established channels. Allow professionals to verify information before disseminating news. The potential for a public spectacle exists. Imagine twilight observations in mid-December, a faint smudge gradually appearing in telescope eyepieces, growing brighter night by night. Amateur astronomers posting images online, a buzz building on social media, and mainstream news outlets picking up the story. An interstellar visitor glowing mysteriously. This represents cultural impact. This is what a bright, peculiar object does to the public imagination. It compels people to look upward and to pose fundamental questions. Why is it blue? Where did it originate? Are we alone in the universe? Even if 3i Atlas fades and proves disappointing, the endeavor itself provides valuable lessons in observing interstellar objects. We learn what methods are effective, which are not, how to coordinate observation campaigns, and how to allocate resources for rare transient events. Future interstellar visitors will benefit from the lessons learned here, and visitors will continue to arrive. Oumuamua demonstrated their existence, and 2i Borisov confirmed it was not an isolated incident. 3i Atlas is the third such object. There will undoubtedly be a fourth, a 10th, and even a 100th. Each one offers instruction and refines our observational techniques. December 19th. Mark your calendars. By Christmas, we will know whether 3i Atlas continued to brighten or has faded into obscurity. By New Year's Day, we will possess spectral data. By February, scientific papers debating its implications should be forthcoming. The narrative is far from concluded. Perihelion represented Act 1. December constitutes Act 2. The climax is imminent, and the implications extend beyond a single object or a solitary mystery, reaching into the future of how we study the cosmos. This leads us to our next topic. Part 10 explores the broader implications for the science of interstellar objects. Shifts in established thinking occur when anomalies mount. The object designated 3i Atlas could represent another such instance, compelling us to revise our classifications of cosmic travelers. For generations, we've sorted celestial bodies into straightforward categories: asteroids versus comets, rocky versus icy, active versus dormant. These groupings served adequately when our focus was limited to our own solar system. However, visitors from beyond our stellar neighborhood do not adhere to our imposed classifications. Oumuamua exhibited characteristics of both asteroids and comets, along with an unexpected acceleration. Boris, on the other hand, was unmistakably cometary, displaying familiar chemical compositions and conventional behaviors. 3i Atlas defies simple categorization, exhibiting cometary traits like a volatile, rich coma, but differing significantly in brightness and hue. Our updated classification system requires categories beyond simple binary distinctions. These could include cometary interstellar objects that behave predictably, asteroid-like interstellar objects that remain inert, hybrid entities with mixed characteristics, and perhaps a fourth category for objects that do not align with natural models, either due to exotic natural phenomena or because they are artificial in origin. Designating this fourth category carries political implications. Labeling them anomalous interstellar objects sidesteps assumptions about their origin, while techno-signature candidates invites controversy. Regardless, acknowledging the existence of such a category is a scientifically responsible stance. This has direct implications for the design of astronomical surveys. Current observational programs, such as Pan-STARRS, the Catalina Sky Survey, and the forthcoming Vera C. Rubin Observatory, are designed to detect transient phenomena by tracking the movement of asteroids and comets against the backdrop of stars. The detection rate for interstellar objects is presently low due to their rarity and rapid motion. Initial projections indicated that current surveys might detect one such visitor annually. The Rubin Observatory is expected to improve this figure to approximately 5 to 10 per year, but detection is only one part of the challenge. Characterization constitutes the other. Most interstellar objects will be identified mere weeks or months before their closest approach to the Sun, leaving a limited window for subsequent observation. Some, like 3I Atlas, are discovered at greater distances, allowing for extended observation periods. While this is ideal, it is uncommon. Mission planning must incorporate provisions for rapid response, opportunistic targeting, flexible scheduling, and coordinated efforts involving both ground-based and space-based assets. Investing in these capabilities will yield significant returns when the next unusual visitor arrives. Fields such as materials, science, and astrochemistry will also require updates. Current models of cometary volatiles primarily focus on water, carbon monoxide, carbon dioxide, methane, and ammonia, molecules observed in solar system comets and interstellar clouds. However, interstellar space is characterized by remarkable chemical diversity. Different stellar environments can lead to distinct ice chemistries, including the potential for supervolatile-rich comets, refractory organic-rich bodies, and carbon-dominated matrices, all of which are plausible scenarios. Expanding our understanding of volatile and refractory substances necessitates laboratory work, including measurements of sublimation curves, fluorescence spectra, and thermal properties of exotic ices and organic compounds. Furthermore, sublimation models under extreme radiation conditions need refinement. Close to perihelion, solar flux is intensely high, with ultraviolet photons capable of breaking down molecules. Thermal gradients drive subsurface fluid movement, leading to pressure buildup. Existing models are adequate for water ice at moderate temperatures, but struggle with supervolatiles under intense radiation. 3I Atlas pushes these boundaries, testing the predictive power of current models. If they falter, it will necessitate iteration and the incorporation of previously neglected physical processes. Non-Earth-like chemistries are significant. Life on Earth has shaped our perspective towards carbon, oxygen, nitrogen, and water. However, comets are not constrained by biological considerations, and interstellar comets even less so. Exotic molecules, polymers, and organic compounds that have not yet been synthesized in laboratories may be prevalent elsewhere. Spectroscopic observations that reveal unfamiliar emission lines will compel us to identify new compounds, thereby broadening the known inventory of cosmic chemistry. Improvements in survey strategies should prioritize the observation of short-duration phenomena occurring near the Sun. Coronagraph networks are currently undervalued. The SOHO and stereo missions, initially designed for solar physics research, have incidentally led to the discovery of thousands of comets. Dedicated constellations of coronagraphs optimized for transient object detection could reliably identify objects like 3I Atlas. Small satellites equipped with wide-field coronagraphs strategically positioned at Lagrange points would provide continuous observational coverage. The associated costs would be modest compared to flagship missions, while the scientific return would be substantial. Rapid response telescopes and robotic systems capable of slewing to targets within minutes are essential for enabling early spectroscopic analysis. By the time observational schedules are manually arranged, critical time windows may have already closed. Autonomous systems reduce latency, thereby maximizing scientific yield from fleeting events. Ground-based networks like Atlas and the Zwicky Transient Facility exemplify this approach. Expanding such networks globally would ensure round-the-clock coverage. Policy considerations and communication strategies are also vital. The manner in which scientists convey uncertainty significantly influences public perception. Oumuamua demonstrated that ambiguous findings can be sensationalized, with headlines proclaiming alien probes, while scientific papers emphasize the need for more data. 3I Atlas appears to be on a similar trajectory. Responsible communication involves clearly articulating what is known, what remains uncertain, and what is speculative, while explicitly labeling hypotheses as such rather than presenting them as definitive conclusions. It is important to counter sensationalism without stifling legitimate scientific inquiry. The mission concepts this necessitates include rapid deep space interceptors. Imagine a small satellite on standby, ready for deployment upon the detection of an interstellar object. While delta-V requirements for intercepts are substantial, they are not insurmountable. Concepts such as the ESA-approved Comet interceptor mission demonstrate feasibility. Adapting this concept for interstellar targets would require faster response times and higher velocities, but would utilize similar technological frameworks. A constellation of small probes could rendezvous with an interstellar visitor, allowing for in-situ sampling of its composition, imaging of its structure, and measurement of its properties. The data returned would provide definitive answers, eliminating ambiguity. High-cadence solar coronagraph constellations represent a more cost-effective and practical near-term solution. Deploying a dozen small satellites equipped with coronagraphs throughout cislunar space or at Lagrange points would offer redundant coverage of the inner solar system. When objects pass close to the Sun, multiple spacecraft would observe them simultaneously, enabling parallax measurements, multi-wavelength coverage, and cross-calibration. The cost per satellite would be in the tens of millions, with the total constellation cost remaining under $1 billion. This contrasts sharply with flagship missions, which can cost billions for the study of single targets. Cultural exploration is also a downstream consequence. If 3I Atlas were confirmed to be artificial in origin, humanity's worldview would undergo a profound transformation. The realization that we are not alone and that intelligent life exists beyond Earth would reshape philosophy, religion, scientific funding priorities, and international cooperation. Even if its origin is natural, the mystery surrounding its behavior serves as a potent reminder that the universe holds countless surprises. Humility is an appropriate response, and curiosity is essential. Our current models are provisional, and nature, or perhaps another intelligence, continues to teach us. The second act concludes with unresolved tensions, unexplained brightening without a clear propulsive force, emissions without fragmentation, and a blue hue without confirmed molecular identification. The question of natural versus engineered origin remains unsettled. These unresolved issues set the stage for the third act, where we broaden our context by linking 3i Atlas to other scientific anomalies and discoveries of 2025. Science does not occur in isolation. Breakthroughs tend to cluster, anomalies cross-pollinate, and understanding one mystery often illuminates others. Part 11. James Webb and Hubble Discoveries. Highlight. The James Webb Space Telescope continues to deliver surprises. 2025 brought detections that no one had anticipated. Analysis of exoplanet atmospheres by Webb's near-infrared spectrograph revealed unexpected molecular signatures. In one system, methane absorption bands were observed alongside oxygen, a combination that thermochemical models suggest should not persist in equilibrium. Researchers are now scrambling to explain disequilibrium chemistry, driven by photochemistry or vertical mixing. Another system displayed emission features tentatively attributed to complex organic molecules, compounds too heavy to be expected in the atmospheres of hot Jupiters. If confirmed, these organic molecules would challenge formation theories and suggest chemical pathways previously overlooked. A methodological parallel exists between these findings and 3i Atlas. Both involve remote spectroscopy yielding surprising results, and both necessitate rapid revisions of existing models. Webb's high-resolution infrared spectroscopy detects molecules by their characteristic absorption or emission lines, a principle similar to how coronagraphs perform color photometry, albeit with far greater precision. When molecules appear that do not fit established templates, scientists question their underlying assumptions. Are the observed spectral lines genuine or artifacts? Are the calibration procedures accurate? Are the models incomplete? Exoplanet atmospheric retrieval codes work by inverting spectral data to infer composition, temperature, and pressure profiles. These codes rely on assumptions about specific physical and chemical processes. When these assumptions are violated, retrievals yield nonsensical results or flag inconsistencies. The spectrum of 3i Atlas, once obtained in December, will undergo a similar analytical process. Spectral lines will be compared against databases, and any anomalies will prompt new hypotheses. If familiar molecules adequately explain all observations, confidence in a natural origin will increase. Conversely, the appearance of unfamiliar features will multiply the questions. Practical synergies exist between these fields. Techniques developed for exoplanet atmospheres, such as forward modeling, emission and absorption spectroscopy, Bayesian retrieval, and error propagation, are directly applicable to the spectroscopy of small solar system bodies. Software tools are transferable, and expertise can be shared. Collaborations between exoplanet scientists and solar system astronomers can accelerate progress. 3i Atlas could benefit from this cross-pollination of knowledge, adopting analytical methods proven effective on exoplanets. The cultural dimension is also significant. Public reaction to unexpected scientific discoveries on social media tends to escalate rapidly. Webb's exoplanet findings generated headlines such as "Strange molecules detected in alien atmosphere," while 3i Atlas is prompting reports of a mysterious interstellar comet glows blue. Both phenomena fuel curiosity but also risk oversimplification. Scientists respond by providing clarification, context, and tempering hype without discouraging enthusiasm. Striking this balance is challenging. Excessive caution can lead to a loss of public interest, while being overly bold can undermine credibility if findings do not hold up to scrutiny. The current era benefits from advanced observatories capable of capturing surprises early. Webb was launched in 2021, and the Rubin Observatory is commencing operations. Next-generation radio telescopes, such as the Square Kilometre Array, are also coming online. We are entering an era where instrumental capabilities are outpacing theoretical preparation, making surprises increasingly routine. 3i Atlas is one beneficiary of this trend. Coronagraphs, despite being an older technology, provided data unobtainable by ground-based telescopes. Future visitors will benefit from even more comprehensive coverage. The pipeline from detection to characterization to understanding is shortening annually. Part 12. Pulsar Timing, Array, Gravitational Wave Background Update. In 2023, the Nanograv Collaboration and International Pulsar Timing Array projects reported tentative evidence of a stochastic gravitational wave background. Through 2025, further observations have strengthened this signal. Gravitational waves at nanohertz frequencies induce correlated timing residuals in pulses emitted by distant pulsars across the sky. These arrays monitor dozens of millisecond pulsars, precisely measuring pulse arrival times to within nanosecond accuracy. Deviations from predicted arrival times, which exhibit correlations between pulsars according to specific angular patterns, indicate the passage of gravitational waves that are stretching and compressing spacetime as they propagate through the solar system. The detected background signal is likely generated by supermassive black hole binaries, pairs of black holes orbiting within the cores of distant galaxies. Population models predict that such binaries continuously emit gravitational waves, creating a stochastic background. However, the observed amplitude exceeds that predicted by some models, necessitating a re-evaluation of black hole merger rates, galaxy evolution, and the dynamics of friction within galactic nuclei. A conceptual parallel exists between these findings and 3i Atlas. Both involve the detection of faint, unexpected signals within noisy data, requiring years of meticulous observation and statistical analysis. Both phenomena challenge existing theoretical frameworks. Pulsar timing arrays have opened a new low-frequency observational window onto the universe. Coronagraphs, while employing older technology, have provided a unique perspective on perihelion events that are obscured from Earth. Frontier science yields significant rewards when researchers diligently listen for faint anomalies and treat them with seriousness. The pulsar timing anomalies could have been dismissed as instrumental noise. However, collaborative efforts led to their rigorous investigation. The redundancy provided by dozens of pulsars and multiple observatories ensured that the observed signal was not a localized interference. Similarly, the coronagraph detections of 3i Atlas gained credibility through redundancy across 3 independent spacecraft. Both instances demonstrate how cross-checks validate or refute scientific claims. A broader epistemological lesson applies. Prepare for anomalies, build redundancy into detection systems, and avoid reflexively dismissing outliers. History is replete with examples of unexpected signals that have revolutionized scientific fields. Pulsars themselves were initially unexpected discoveries. Quasars and gamma-ray bursts were also surprising findings, each opening entirely new avenues of research. While gravitational wave backgrounds and interstellar comet brightness anomalies may seem disparate, they share a common discovery culture, one that anticipates surprise and upholds rigorous investigation. Part 13. AI-driven sky survey anomalies. Each night, the sky undergoes subtle, imperceptible changes, and it is now machines that are the first to notice. Across the globe, machine learning algorithms meticulously examine millions of astronomical images, comparing them pixel by pixel against those from previous nights. Their objective is to detect the unexpected, a flash, A flicker, a movement, any indication of novelty where previously there was nothing. This process, known as transient detection, has evolved into one of the most data-intensive and automated frontiers of modern astronomy. The Zwicky Transient Facility, ZTF, at Palomar Observatory in California is a leading participant in this endeavor. Every night, its wide-field camera surveys the entire northern celestial hemisphere, generating over a terabyte of imaging data in a single observational session. Each image is immediately processed by AI-driven pipelines that subtract older reference frames, thereby revealing any changes that have occurred. These changes could signify a supernova, a near-Earth asteroid, or a faint variable star exhibiting periodic flickering. While most of these detections are routine, the algorithms occasionally flag something unusual, a transient event that deviates from all known categories. Its light curve may not follow the expected pattern, or it might move too erratically for a typical comet. These are the moments of critical importance, the rare outliers that may point to something genuinely novel in the universe. This automation is indispensable as human capacity to process such vast data sets is simply insufficient. The upcoming Vera C. Rubin Observatory in Chile, poised for full operational status in the near future, will collect up to 20 terabytes of data nightly, cataloging billions of celestial objects. Even with thousands of astronomers, no human team could meticulously inspect every individual light curve or motion track. This is where artificial intelligence assumes its role, tirelessly sorting, classifying, and ranking every anomaly. However, there is a crucial caveat. AI can accelerate discovery, but it can also generate convincing illusions. Machine learning models, particularly neural networks, excel at identifying patterns for which they have been trained. For instance, a network trained on known comets learns to anticipate specific behaviors, such as gradual brightening, consistent color changes, and predictable tail evolution. Yet these same systems often falter when confronted with phenomena that are truly novel. When an object behaves outside established parameters, for example, brightening 7 times faster than anticipated or shifting to a bluer hue than the sun, the system may exhibit hesitation and confusion. It is unable to readily interpret what it is observing. This is precisely where 3i Atlas enters the narrative. Imagine an early warning system trained on tens of thousands of comet-like light curves. Every known comet, both from within and beyond our solar system, contributes to its neural model of normal behavior. Then, one night, data streams in from the SOHO or stereo spacecraft, revealing an object whose brightness scales not according to the expected r to the power of 4, the classic comet law, but closer to r to the power of 7.5, an absurdly steep curve. The algorithm compares this observation to its database, assigns an anomaly score, and flags it for human review. Within hours, astronomers receive an alert, an interstellar object exhibiting behavior unlike any comet previously documented. This is where the speed of AI becomes a distinct advantage for humanity. Machines can process and cross-reference data from multiple observatories within minutes, a task that would take human analysts days. In the realm of transient astronomy, mere hours are significant, as many phenomena such as outbursts or disintegrations unfold on that timescale. If 3i Atlas were to suddenly fragment or expel a luminous plume of gas, automated systems could capture the event in progress rather than merely documenting its aftermath. The Catalina Sky Survey, the Atlas Network, and ZTF have already demonstrated the efficacy of this approach. They rely on anomaly detectors and real-time alert systems that trigger rapid follow-up observations globally. For 3I Atlas, similar systems may have been responsible for the earliest reports of its anomalous brightening during perihelion, when it would have been obscured behind the Sun. Furthermore, AI not only flags anomalies, but also filters out noise. Coronagraphs and heliospheric imagers, such as those aboard GOES 19 and SOHO LASCO, are notoriously challenging to interpret. They capture light scattered through the solar corona, which is replete with streaks, cosmic ray impacts, and instrument artifacts. Over decades, machine learning models have been trained on these datasets to identify and remove false signals, the optical ghosts created by the sun's glare. Neural networks can learn the characteristic patterns of electronic noise or internal reflections, thereby significantly improving the signal-to-noise ratio for faint objects located near the sun's limb. Without this capability, the faint blue envelope of 3I Atlas might have been dismissed as a camera glitch. This is where speculation begins to emerge, the kind that keeps both scientists and dreamers awake at night. What if anomaly detection systems could achieve more than simply finding supernovae or asteroids? What if, one day, they could identify signals that do not appear astrophysical at all? This is not mere science fiction. Modern pipelines already perform spectral anomaly detection, analyzing thousands of light curves for unusual periodicities or narrow-band emissions. The brightness variations of a natural star or comet typically follow well-understood physical rhythms. However, if an object emitted light at non-astrophysical frequencies, or if its pattern of brightening repeated with mathematical precision, AI could flag it as non-natural, even if human eyes failed to perceive it. Imagine applying this to interstellar objects. Suppose a future visitor akin to 3I Atlas exhibited modulated emission, subtle repeating pulses, or reflectivity changes inconsistent with rotational gas jets. The algorithm would not inherently recognize it as artificial, it would simply flag it as a high-priority anomaly. The subsequent question would then shift from "what is it?" to "who built it?" This represents the speculative frontier of technosignature searches, and it is not as far-fetched as it might initially sound. The Breakthrough Listen project already utilizes deep learning systems to scrutinize radio spectra for unusual signals. Optical astronomers are beginning to adopt similar approaches with light curves, searching for artificial flickers among billions of natural ones. AI is indifferent to the reason for an anomaly. It simply detects its presence. Visually, envision a network of automated observatories comprising orbiting telescopes, ground-based cameras, and solar monitors, all interconnected by AI pipelines. Each night, thousands of potential anomalies are streamed in. The AI sorts them based on their statistical unusualness, prioritizing the most exceptional for rapid follow-up. Within minutes, astronomers can decide whether to initiate an emergency follow-up observation, directing instruments like the Hubble Space Telescope, the James Webb Space Telescope, or a major ground-based telescope toward the event. The stakes are considerable. A false positive would consume precious time and resources, whereas a missed detection could mean forfeiting one of the most extraordinary discoveries in decades. This delicate balance between sensitivity and specificity, between detecting everything and avoiding false alarms, constitutes one of the central challenges of AI-driven astronomy. The process relies on the fine-tuning of algorithmic parameters, the careful selection of training datasets, and continuous feedback loops between artificial and human intelligence. Fundamentally, it represents a discourse between two distinct forms of cognition, one rooted in computation, the other in intuition, each illuminating the other's understanding of what constitutes the unconventional. In this evolving scientific frontier, celestial bodies like the object designated 3I Atlas serve as ideal subjects for scrutiny. They reside at the periphery of our conventional knowledge, compelling both human researchers and machine learning systems to broaden their definitions of what is achievable. When a visitor from beyond our solar system appears, exhibiting a luminosity that surpasses any known comet and a hue bluer than our Sun, the computational models not only flag this as an anomaly, but prompt a profound question. Are we witnessing the extreme manifestations of nature, or something that transcends our current comprehension of the natural world itself? In this regard, artificial intelligence has transcended its role as a mere instrument. It has evolved into a novel form of astronomical perception, one that is unfaltering, tireless, and possesses perfect recall. As the cosmos becomes increasingly rich with data, it will be the computational systems that first discern when the universe unveils something entirely unforeseen. Part 14. Update on a groundbreaking mission announcement. Concepts for rapid response interceptor spacecraft began gaining momentum within mission planning discussions in the year 2025. Proposals were submitted to NASA, the European Space Agency, ESA, and various private philanthropic organizations detailing plans for small satellite interceptors designed for swift deployment upon the detection of interstellar objects. The required changes in velocity, or delta V, are contingent upon the target object's trajectory. Bodies traversing the inner solar system necessitate less delta V compared to those that maintain orbits in the outer regions. A typical interception mission demands a velocity adjustment of between 5 and 15 kilometers per second beyond Earth's gravitational escape velocity, a feat achievable through ion propulsion systems or chemical booster stages. Technical specifications include onboard spectrometers capable of analyzing visible and infrared wavelengths, cameras designed for imaging at multiple resolutions, mass spectrometers for determining composition, and dust collectors for gathering particulate matter. A continuous data relay to Earth is essential for communication. The duration of such a mission, from its launch to the point of encounter, can range from several months to multiple years, depending on the target's distance and relative velocity. Power for these craft would be derived from solar panels when operating in proximity to the Sun, and from radioisotope thermoelectric generators, RTGs, when positioned in the colder outer reaches of the solar system. In relation to the 3I Atlas object, an Agile mission could have been launched in August, the same month the object was discovered, enabling it to reach its perihelion for a close flyby. Instruments aboard would have been able to directly sample the coma's composition, image the nucleus with meter-level resolution, and measure non-gravitational forces in situ. The data thus obtained would have resolved ambiguities, eliminating the need for conjecture based on photometric measurements or brightness laws. Direct empirical evidence would have provided definitive answers. Established mission precedents already exist for such endeavors. The Comet Interceptor, approved by ESA for launch in the year 2029, exemplifies this concept. It is slated to rendezvous with a long-period comet during its initial inbound trajectory, studying pristine material. The DART mission, which successfully impacted the asteroid Dimorphos, demonstrated the feasibility of rapid targeting capabilities. Previous missions, such as those that returned samples from asteroids, have proven that sample return is achievable for small celestial bodies. Integrating these combined capabilities into an interstellar interceptor is technologically within reach. What is presently lacking are concrete funding commitments and the necessary infrastructure for rapid launch. Political and financial realities present obstacles. Space agencies are often hesitant to allocate funding for single-purpose interceptors aimed at targets of opportunity, as budget cycles are typically protracted. Interstellar objects, by their nature, arrive without predictable timing. Proponents advocate for the deployment of small satellite constellations as a more adaptable solution. This would involve keeping a number of spacecraft fueled and in readiness in designated orbital positions. Upon the appearance of a target, the nearest available spacecraft would be launched. This approach disperses the cost across numerous potential missions, thereby mitigating the risk associated with the failure of a single target intercept. The total cost of such a constellation, estimated to be under $1 billion, would be significantly more affordable than flagship missions that often cost several billion dollars. A cinematic depiction of such a mission might envision mission control during the intercept phase. Engineers would monitor telemetry data as the spacecraft approaches the 3I Atlas. Cameras would capture images revealing the nucleus's structure for the first time. Spectrometers would record spectral data in real time. Dust collectors would deploy, gathering particles. Subsequently, the flyby would conclude. The spacecraft would continue its journey, transmitting its collected data. Teams would then analyze these findings, with results potentially being published weeks later, effectively solving the mystery. This represents the ideal scenario. The reality, however, involves inherent risks, potential failures, and necessary compromises. Nevertheless, the engineering challenges are surmountable. The primary constraints are political will and financial resources, not the fundamental laws of physics. Part 15. Quantum Fundamental Physics. Surprise and Final Synthesis. Experiments conducted aboard the International Space Station in the area of material science in the year 2025 yielded observations of unexpected behaviors under microgravity conditions. Crystallization processes resulted in the formation of structures that diverged from predictions made by ground-based models. Quantum fluids exhibited phase transitions at temperatures that differed slightly from theoretical calculations. These subtle shifts suggest that refinements are necessary for many-body quantum theory, or that certain environmental factors, previously unaccounted for, are influencing the outcomes. Experiments focused on the direct detection of dark matter have narrowed down potential parameter spaces but have not yet yielded a definitive signal. While each of these results, taken individually, may not be paradigm-shifting, they collectively contribute to a more precise understanding of fundamental physics. The overarching lesson points to an era defined by scientific surprises. Anomalies observed across diverse fields, including astronomy, gravitational waves, AI-driven detection, mission design, and quantum experimentation, collectively indicate a period where the sensitivity of our instruments is surpassing our theoretical expectations. We are detecting phenomena before we fully comprehend them. The 3I Atlas fits this pattern, representing yet another anomaly in a period already rich with them. Synthesizing the leading interpretations for the 3I Atlas involves subjectively assigning plausibility rankings offered illustratively. 60% probability is attributed to natural exotic chemistry. This remains the baseline hypothesis, suggesting unusual composition, supervolatiles, or extreme but explainable phenomena. 30% probability is assigned to data artifacts, such as errors in instrument calibration, issues with background subtraction, or coincidental biases across multiple instruments. While a low probability, it cannot be entirely dismissed until a comprehensive vetting process is complete. 10% probability is assigned to an engineered origin. This remains a speculative hypothesis, with its low prior probability being only slightly updated by the anomalous observations, not enough to significantly influence the posterior probability. These percentages are meant to be illustrative rather than rigorous. Individual scientists would likely assign different weightings based on their pre-existing beliefs and the evidence they deem most compelling. Final hypothetical scenarios offer potential resolutions. Scenario 1. A confirmed exotic comet. Scientific papers published in March 2026 would confirm a supervolatile composition, identify specific molecular emission lines, and explain the observed brightness curve through fragmentation models. Textbooks would be updated, and the study of cometary chemistry would expand to include carbonaceous interstellar visitors. 3I Atlas would then be catalogued as an unusual, yet natural, celestial object. This would represent a progression in scientific understanding. Scenario 2. A confirmed engineered fragment. Spectroscopic analysis would reveal narrow-band emissions inconsistent with any known molecules. High-resolution imaging would reveal geometric structures, planar surfaces, and symmetries. Independent research teams would replicate these findings. Scientific papers would be published, sparking widespread media attention and initiating a profound philosophical and scientific revolution. SETI priorities would shift, and funding would surge for subsequent missions. Humanity would confront confirmed evidence of extraterrestrial intelligence, even if indirect or ancient, leading to a transformation in culture. Scenario 3. An artifact of the instruments. Detailed calibration reviews would uncover correlated errors in all 3 coronagraphs. Stray light, combined with vignetting and misestimations of background noise, would have produced the apparent blue color and steep brightness curve. The actual object would have been fainter and of a neutral color. Claims related to a normal comet would be retracted by the scientific community. This scenario would serve as a cautionary tale, imparting valuable lessons about the limitations of coronagraph technology. 3I Atlas would then fade from public consciousness as science self-corrects. A call to action is issued for the public and amateur astronomers. Observe safely. Verify coordinates from authoritative sources like the Minor Planet Center or NASA JPL Horizons. Utilize applications to locate the object in the sky. Report observations to established networks rather than social media platforms initially. Place trust in verified data channels. Exercise patience. Scientific inquiry requires time. Hype may spread rapidly but dissipates quickly. Truth, however, emerges slowly and endures. The 3I Atlas can be framed as a profound mystery, testing our instruments, our theoretical models, and our collective patience. Regardless of the ultimate explanation, whether natural, artificial, or an instrumental artifact, this celestial visitor has compelled us to reevaluate our definition of the ordinary. We are reminded that the cosmos is vaster, more enigmatic, and more astonishing than our current models can fully encapsulate. Humility is a fitting response, while curiosity serves as our driving force. The next interstellar visitor is already en route, unseen, carrying its own unique secrets. We will be prepared, we will observe, we will analyze, we will learn. This is our endeavor. This is the essence of science, the relentless pursuit of truth through empirical evidence, irrespective of where it leads, how uncomfortable it may be, or how wondrous it ultimately proves to be. The 3I Atlas has bestowed upon us a gift, the gift of mystery. And mysteries are, by their very nature, invitations to discovery.